Hello everyone and welcome back to the Kohi Game Engine series. Today we're going to take a look at point lights and we're going to add a little bit of debug functionality. So before we jump into the video, I would like to take a quick minute and thank the partners of the channel. The partners are the highest tier support both on YouTube and Patreon, and they are Caden, Eearslya, Gerboles Inc., Kyla, Super Awesome, and Wensheng. I'd also like to thank all the other fine folks that appear on the screen here. Your support is greatly appreciated. Thank you very much. If you'd like to support the channel and support my work, feel free to have a look at the YouTube membership, or if you prefer Patreon, you can check out patreon.com/TravisVroman. Okay, so point lights. Let's start with what the definition of a point light is. A point light is simply a light that radiates from a given point in space. Typically, this might be something like an individual light in a room, for example. And light casts out from it in all directions, and of course, it can be placed around the scene. Point lights are a very useful type of light, and probably will be the most used of all the light types that we're going to support. So there's not a whole heck of a lot to implementing point lights, so I am also going to add something else to this video as well, which will be a little bit of a handy debug feature to kind of show the way that this stuff works, as well as troubleshoot any issues should they arise down the road. So the first thing I actually want to look at is I want to take a look at the debug functionality itself, and then we'll go ahead and add in the point light afterwards. And so the debug functionality that we're going to be adding is the ability to change the given render mode. And what do I mean by render mode? So you may recall that some time ago we added this int mode to our global uniform object, and we never really set it. We never wound up using it. We sort of just passed it off to the shader, and that was it, right? We just kind of added it and didn't really mention what it was going to be used for. So what we're going to support is a couple of different ways of rendering our geometry in the world to the screen. First off, we're going to have something that we're going to call our standard mode, which is basically going to be what we have now. It's going to show us all of our textures, our standard lighting, things of that nature. The next thing that we're going to have is what I'm going to call normal mode, and that's going to change out all the colors with normal information in the scene. So it's going to allow us to visualize the normals in a scene, taking into account the normal maps as well as the facing of the geometry. And that'll make a little bit more sense once we actually get to that point. And then we're also going to have a lighting only mode where we don't actually render any of the texture information. We just use the normal and spec maps along with the lighting information, and we just render lights in the scene, along with the geometry, of course. And this will allow us to debug any lighting issues that should come up along the way. And we'll be adding additional modes to this as we build on it, but this should be a decent way to start building up this feature. And so there's a couple things we're going to need to fix to actually implement this right off the bat. So the first thing is actually going to be in our input .h. We are going to need to add keys for the top row of numeric keys on the keyboard, because we don't actually have key codes for this, and we actually need a way to bind these. Now, for Windows users, we can just use the character codes as they are, but it doesn't quite work out that way nicely in all OSs. So for at least the Linux platform, I ran into some issues around not having these defined, as well as an additional change that we're going to have to make. So this kind of gives us the flexibility of doing it either way. So we have key 0 through 9, and that represents the keys along the top above the letter keys on your keyboard. So we've added those here to our keys enumeration. So that is the first change. And then the second change is actually going to be Linux specific. So if you're on Windows or Mac, you can actually skip this portion. Although you may actually wind up having to do this on Mac as well. I'm not 100% sure. But at least for now, I'm going to implement this in the Linux layer. And that is, in our translate key code, we actually need to add the cases for those keys here, because the default for this actually returns 0. So the problem with that is, because we didn't have these registered here, our key presses for those would always come up as just the literal character 0, which is not useful. We couldn't actually get those keys to work. So just a tiny tweak here within Platform Linux. And then there's also one more tweak that we need in this file. And this is around line 210 or so. 211 or so, actually. 211. We're actually going to take out this shift mask, because for some reason for me it was causing some issues. I need to do a little bit more research on this, because this isn't all that well documented on why it was behaving this way, but I was basically getting some really funky codes returned to me for the numeric keys. And shutting this off just seemed to fix that issue. So I've gone ahead and commented this out, and I'm just passing 0 for this last field here instead. And this seems to work okay for now. So if any of you guys are aware of what that could be, feel free to let me know in the comments down below, and we can discuss it. Anyway, so those are the only changes in terms of the platform, but they are kind of important ones, because without them, this new debug system will not work, at least on Linux. So with that, there is a change in the shader configuration. So we'll go here to our built-in material shader config. We have added a new global uniform. It's going to be called mode, and it's going to be a type of U32. U32 is probably overkill for this, but it's just a standard integer type. We'll use it for now. We may wind up swapping that out for a smaller type and or packing more values into that, but for now, we're just going to use that as is. So we've added that there. Our material system will obviously need an update to support this as well. So if we have a look at our material system, all the way at the top, we now store something for the render mode. And I just called that render mode to separate it from model a little bit, because mode and model are only one letter apart. So it was getting, it might be kind of hard to miss a potential issue there. So I've gone ahead and called this render mode. And I've gone through the same process of defaulting it to an invalid ID, which is here. And the same thing down here as we've done with all of our other uniforms is I've gone ahead and grabbed the index, the uniform index of that. And then, of course, our apply global has another new argument, which is just a U32 render mode. And this one's not a pointer because we're just passing a flat number here. So the render mode gets passed in here, and it gets applied to the index at render mode. So the only difference here is, because this requires a void pointer to be passed, we just pass the address of render mode here. So that is pretty much it for the material system. Obviously, this means that we updated the H file as well with that. The next change is, since we are going to be using our event system, in event.h, we have gone ahead and added a new event for this. We've given it its own explicit one instead of using one of these debug codes, just because this is something that we're probably going to want to leave in the engine. It is debug, so maybe on release builds we will comment this out, but at least for now we want to leave it in. So we've given it its own code, and basically the way that this works is we pass the render mode event and an I32 for the mode. And the code for that is 10. Okay, so the next thing that we are going to take a look at is the renderer front end. Go to the top here. So we also hold a render mode within the render system state because it makes sense to go ahead and define that here. and keep that within the render itself. Within the render on event, within the render itself, we have this new render on event private function, which is a callback for our event. So it takes a code, sender, listener instance, and context. It switches on the code that's passed through. And right now we're only looking at the event code set render mode. So we go ahead and take that. We cast the render system state, get that from the listener instance. And then we go ahead and parse the mode out from that. We take a look at the case and just output some debug information, set the render mode to the render mode that was passed through. Technically, we don't need this case statement. We could just assign this directly, but I've done this here just to give us a little bit of console output, just so that it's a little easier to tell what's going on. So our render mode default is defined as 0. Our render mode lighting is defined as 1, and our render view mode normals is defined as 2. That definition exists in render types INL here as an enumeration. So once we've applied those things, the event is considered handled, and we go ahead and return true. If we pass any other code to it, of course, it returns false. Down here, where we're standing up the renderer, we go ahead and we set the default mode to render view mode default. And of course, when we apply the globals to the material shader, this is where we are going to pass in the state pointer render mode. And when we come down here to material system apply global for the UI shader ID, we're actually not using mode here, so we're going to go ahead and pass 0 for this. If we ever do have a mode for the UI shader, we will probably wind up implementing different modes for each one of those codes. And so we'd store that as a different integer and pass a different property here. So since we're not using it for now, we're just going to follow suit and pass 0. And that is it for the front end. Lastly, for this feature, within the game.c, after our input that we added last time for the P key to output the camera position, we've added some new debug functions here. So basically what happens is if we press the 1 key, we switch over to the lighting mode. If we press the 2 key, we switch over to the normal mode. And if we pass the 0 key, we go ahead and we switch back to default mode. So this just fills out that data and fires off the event, and then the renderer will go ahead and pick it up and switch modes. Okay, so next in our shader itself, we'll take a look at the Vertex Shader first. So in our global UBO, we have our mode that is now being passed in. And then if you recall before, we also have this out mode, which is what passes it over to the Fragment Shader. And now all we do is we go ahead and copy that over. So that is it for that. And now we come to the Fragment Shader, which is what does all the work. So in the Fragment Shader, we can see we've got some other stuff in here already for our point lights. We'll come back to that in a second. But we have our in mode here, which is a flat in int in mode. And before I move on, I should probably mention what this flat means. So most of these types that we've dealt with this far, where our types are vectors, which use floats, are interpolated between one vertex to the next. So if you have red on one vertex and green on the next vertex, the value in between those color-wise is all interpolated from one to the next. And that works great with floats because floats are fractional numbers. But integers are not fractional numbers. Integers are whole numbers. They can't be fractioned out, right? And so we have this flat qualifier here to say this is not something that is interpolated. This is always the same flat integer value. So that is basically what that flat means. It means that this is always going to be the same. So we have that called in mode. And what we do is we use our in mode in here to calculate some things. So the first thing we're going to do is within our main, after we update our normal, we do a check to see if we're in mode 0 or mode 1. So mode 0 is our default, if you recall, and mode 1 is our lighting mode. So if we're in either one of these modes, we actually want to calculate the lighting. So we put all of our calculation code for lighting inside of here. So we've got our view direction here and our out color for calculating the directional light here. We also have the stuff for our point lights here. Again, I'll come back to that in a minute. Otherwise, if our mode is 2, then we treat this a little bit different. What we do here is, since we already have the normal value calculated, taking into account the normal map, what we do here is we actually set the out color to the absolute value of the normal. And so this will give us a RGB value that represents the normal of that current fragment. And we utilize that, since that is a vector 3, we utilize the alpha as 1.0. So everything has a fully opaque value to it. And by setting this information to the output color, if you recall that our normal information lines up with our RGB XYZ values from our normal map, this translates nicely into color and will give us color information on the screen telling us what our normals actually look like. So this will make sense once we actually run the application here in just a moment. So you'll note that if we're in normal mode, we don't actually perform any of these lighting calculations because we don't need them. And likewise, we don't use the normal if we are in one of the lighting modes. So that is how that works. Likewise, our directional light, which technically never gets called, checks to see if we're in mode 0. I did this specifically because we are eventually going to have other modes where we may or may not want to perform parts of this calculation. So there's a good chance this will eventually be removed once we actually start removing some debug stuff, but for now, this is the way I've chosen to handle that. Now, that is all there is to the debug feature. And as you may have guessed, our point lights are going to be completely implemented for now in the Fragment Shader. And again, this is another temporary measure because we want to get this stuff up and running as quickly as possible, and then we want to build our systems around it. And we don't have a lighting system built out yet to actually support this. So we're going to hard code the lighting values in the shader for now, and then eventually we'll be passing them through within buffer data or uniform data or something of the like. So the implementation of our point light looks a little bit something like this. This is the structure that our point lights we use. So point lights, unlike directional lights, do actually have a position because the light radiates from a particular position in space. So we have a vector 3 position. We also define a vector 4 color because that's RGBA. So we can use the alpha value to control the brightness or darkness of that particular light. We also have a constant value, which is typically 1. And this is to make sure that the denominator in the equation never gets smaller than 1. And we'll take a look here in a minute to see how that works out. We also have a linear factor, which reduces the light's intensity in a linear fashion as you move away. So typically with a light, the further you get away from the source, the less intense it becomes. So our linear value will actually cause that to have a linear fall off the further you get away from a light, which is usually close to good enough, but not quite. So our linear gets us most of the way there, but we actually want to add something to that to sort of affect the curve of that fall off a little bit and make it a little bit closer to what is in real life, because it's not quite a linear fall off that you get from point lights in real life as you get away from the light. So we also introduce a quadratic property, which basically makes the light fall off much slower at longer distances. So it falls off really quickly as you get away from the light when you're really close to it, but the further out you go, it falls off a little bit slower. And this tends to be the way that it works in real life as well. And so we have a value there that we can use between the linear and the quadratic to adjust those two. And the constant is what it says it is. It's usually 1. It usually never changes. And in fact, we probably won't even have these properties eventually within the front end itself. They will probably generate these properties, but for now, this is the properties that are required by the shader. Anyway, So we have our structure for our point light. So each point light is going to be represented by one of those. And we have a couple of example lights here. So we have P light 0 and P light 1. So P light 0 is positioned here. It is a green light. So we have RGBA. So it's full intensity green, and it is also fully lit. So here is our constant, 1.0, as we discussed, our linear fall-off rate, and our quadratic fall-off. We also have a P light 1, which is a red light, and has the same linear and quadratic values, but it is positioned somewhere else in the scene. So these are actually positioned at the back corners of our cube in our scene. And this will cause us to be able to see the different lighting from the different corners. So next comes the part that we saw before that I said I'd skip over and come back to, which is the calculate point light. So we treat this light the same as we treated the directional light, where we add everything together because light is additive. And so we call this new function that we have, which is calculate point light, twice. Once for the point light 0 and once for the point light 1. Otherwise, we pass the same normal and fragment information and view and direction. We have our new declaration of our calculate point light function up here. So it takes a point light, it takes the normal, it takes the fragment position, and it takes the view direction. So the calculation for this will be somewhat similar to the way that the directional light works. It just uses a different algorithm. If we scroll down here, we see the code for that. So here's the definition of that function. So first we get the light direction by subtracting the frag position from the light position itself. We go ahead and we retrieve the diffuse factor for that. So that is done by taking the dot product of the normal and the light direction, basically saying how directly is the light actually hitting this particular fragment. And then we go ahead and we make sure that we're not taking in any negative values by just calling max between that calculated value and 0. And then we go ahead and we calculate our reflect direction. This is used for our specular highlights. So this is actually pretty much the same calculation as we did for the directional light, so I'm not going to touch any more on that. Next, we calculate our attenuation, which is the fall off we've been talking about. So attenuation is sort of the technical term for it, where you use the constant, the linear, and quadratic to actually calculate it. And this is the algorithm for that. So you take first the distance, which is the difference between the light position and the fragment position. So you take the length of that. And your attenuation is basically 1 over your light constant plus your light linear times distance plus light quadratic times distance squared. And this is the formula for that. We then go ahead and take in the ambient color. We take the diffuse color, the specular color. We go ahead and we apply the diffuse sampler to the diffuse and ambient, just as we did in the directional light. We apply the specular using the specular map, just as we did up here. So that's all the same thing. You guys have seen that stuff before. We go ahead and work in the attenuation into the ambient, diffuse, and specular. So that just handles that fall-off value we were talking about. And then we go ahead and add up the ambient, diffuse, and specular, just as we've done before, and we return that. That value is then added to our out color. So we do this once for each light, and that's it. We're set. So all we have to do here is run a task post build, and we'll do a clean and build on the code, and we'll go ahead and run. And we see here, nothing really looks too different, for at least from this perspective. But if we move our camera around to the side, towards the back, we can see our green light here. So we can see that our specular is working as designed. And if we move around to the other side, we see our red light. Okay? And now, this is a little bit difficult to sort of visualize. We can change up the texture and maybe see it a little bit more clearly, right? We could see the red over here and the green over here, and that helps a little bit. But let's take a look at these rendering modes that we added. So I press 1, and now it takes away the color information and just shows us the lighting information, which is extremely helpful because it makes it easy to see where the light is actually being applied to. And as we rotate around this, we can see how the directional light affects it as well. So we can come up here to the top, take a look at the top, and see how that sort of looks as it spins around. And it really provides us with a clear way of seeing exactly what's going on. So if you're ever having questions about how your normals are working, we also have a view mode for that, which is the 2 key. And so when we press that, we see what the normal information actually looks like here. Now I should point out that there is positive and negative normal information, but when you're dealing with RGB, you can't really have negative values. So that was one of the reasons that in the code here, I took the absolute value of the normal. So that way, in the positive and negative axis, it's basically going to treat the value the same. So what I mean by that is, if we take a look here at the top, this is the y-axis, which is represented by the green channel. You'll see here that the predominant color is green because most of the normal information on this face is facing straight upwards, which is the y-axis. So we can see here that we have the red that's going along the x-axis and the blue shades that are going along the z-axis. And we can see as this rotates, that takes different portions of the image accordingly. And likewise, if we go to the bottom of the cube, we see that we have the same thing because it's pointing downwards, which is still along the y-axis, but because we're taking the absolute value of that, we are getting basically the same result as the top. If we were to just use the value as is and not take the absolute value, we would get black there because that would basically get clipped off at 0 because you can't render a negative color. So the other thing to point out is if I go ahead and set our camera, in fact, I'm going to rerun this just so I can line it up perfectly. So when we run this and we switch into our normal view, you'll note that as soon as the cube faces the camera directly, it turns blue. And as soon as these faces face left or right, they turn red. And that gives you an idea of what axis the face is actually facing. So you can see that it interpolates in between as it's rotating around, and it just gives us a nice way to sort of be able to visualize this. Now this is using the default normal texture because we haven't actually swapped out the texture, but if we go ahead and do that, we can see here that we get the different normal information for the next texture in line. And so this gives us a very quick way to be able to verify and validate that our normals are actually correct and doing what is expected. So another thing to point out is, since we know that green is up on this, if we take a look at our normal values here along the top edge of these bricks, we actually see that there is green, and the bottom edge is technically showing green too. So we know that the normals are actually being calculated correctly and are being placed correctly within the world. So with that said, that is going to wrap it up for this video. We are making some pretty decent visual progress in these last few videos, so I hope you guys are liking the direction that we're taking this. It's certainly starting to have a little bit of a more game-like appearance in terms of being able to render some graphics that are a little bit more dynamic. So anyway, that is going to do it for this video. Thank you guys so much for watching. If you like this video, please toss it a thumbs up. If you haven't already, consider subscribing. Click the little bell icon there to get notifications as to when videos in this or other series drops, and I will see you guys next time.